back to week 8, day 2. Yeah, I'm pretty sure this is wrong, right? What you're supposed to be doing is looking at the 3 squares to your right and then picking the one that was closest in elevation to your current square. A lot of you guys noticed the code was crashing, and the reason for that is because there's 2 reasons why your code would crash. First of all, if you're not doing your axes aligned to a 4-byte boundary, because remember, you're an integer array. Integers are 4 bytes each. So rather than reading from offset 1, offset 2, offset 3, offset 4, which is wrong, you're going to be at offset 4, 8, 12, 16. A lot of you, myself included, I do it wrong oftentimes the first time as well. I don't multiply by 4, because there's 4 bytes per integer. That was probably the most common bug that I saw with you guys. The second reason why code would crash was because, and I didn't want to tell you guys this because it's a really important skill in computer science to figure out why code is not working. It's something that my code was crashing and I had to figure it out myself, and so you need to hone those skills. You need to develop those skills and figure out why code crashes. In this case, Bridges Mountains 45. In this case, there is a weakness in the Bridges code. The Bridges code. So wherever you're going to draw that purple line, you set the elevation to -1, right? That was your job. And then what they did was they said, here's the Bridges code. If the pixel value is -1, change the color to purple. And otherwise, here we go. Grayscale it. So it takes the value of the pixel, right there. Takes the value of the pixel, multiplies it by 255.0. They didn't put the 0 there, that's fine. That's a float. So pixel value is a float times a float. They didn't technically need to do that, I think. Or, well, yeah. Because that is still a float divided by the maximum value of the array. So, if the pixel value is the maximum value of the array, you get 1. If it's 0, you get 0. If it's in between, it lerps in between. And so, lerping is a really important concept in computer science. We use lerp nodes all the time in game development, all the time, everywhere. It was finally added to the C++ standard in C++ 20 of all things. And so what lerping is, it stands for linear interpolation, but we just call it lerping. So imagine you've got a dial on your car's thermometer. When you turn it all the way down, when you turn the dial all the way to the left, 0, let's call it, the temperature is at 60 degrees Fahrenheit. And when you turn it all the way to the right, 100% to the right, it is at 90 degrees Fahrenheit. Okay? And so as you turn the knob between 60 and 90, it needs to linearly interpolate between 60 and 90. So if you're at 50% of the way, if the knob is pointed up, then this point here needs to be halfway between 60 and 90. Let's make that a better 9. So 60 plus 90 is 150. 150 divided by 2 is 75. So the temperature here would be 75 degrees Fahrenheit. If the knob is at 25% of the way, so kind of like top left corner, you know what I mean? Like there's a little dial and it spins like this. When the knob is 25% to the right, then it will be 60 times 0.75 plus 90 times 0.25. 45. So 67. 67.5 at 25%, and then 82.5. 82.5 when it's at 75%. And so this is, it'll smoothly, you know, if you look at it on a graph, you know, 0, 100, this is at 60 degrees, this is at 90 degrees, and it will smoothly transition from 60 freedom units to 90 freedom units, okay, as you turn the knob up. Now, the question is, what happens if you have a number below 0 or above 100? And that's actually what's causing the code to crash here. So the hardest thing to think about in computer science is the things you didn't think about. And that's what, this is a bug in the bridges code, actually. So they did not consider the fact there could be negative elevations. Okay. And so if you have a negative elevation anywhere on your map, it is going to crash the code. And that's what I was hoping you guys would figure out. Why was it crashing on, you know, some maps and not others? I want you guys to print out the maps, look at them, see out all the things, find out what value is causing this to crash, right? And you know, I just kept, they're like, it's crashing on the construction of a string. It's really not. It's really not. What's causing it to crash is that the color function here, which takes in a number from 0 to 1, doesn't handle negative numbers, and it explodes if you pass it a negative number. So if the elevation, pixel value here, the elevation, if the elevation is below 0, it gives a negative grayscale number, which is outside the range that the color thing takes, and it will crash. Okay. So, yeah, but you didn't need to take CSI40 for this. This is a skill that all of you guys need to develop. Like, why is it crashing, right? And so if we run this, make okay, it didn't compile. Go on. There you go. All right. Let's pull this out real fast. Remind me to put this back in. And so if we run this on Korea, was it crashing in Korea? Then Korea.dat. Yeah, you see how there's negative elevations on Korea? Right. You run it, pass in Korea.dat. Enter the starting row, 30, crash. Okay. And so one clue here is that it's crashing even without you guys writing any code, right? And so there's a reason why I did this intentionally. Like I fixed this bug for the CSI40 people because the CSI40 people are like the baby birds you're pushing out of the nest. You know, you don't want them to crash, you want them to fly. But for you guys, well, you know, welcome to the real world. You will encounter bugs and weird bugs and bugs that aren't necessarily your fault, and you need to be able to identify them. That's why I talk so much about this. You need to be able to zoom in and find, okay, we're crashing on a string. And so a lot of students will be like, well, it's clearly a bug in the string class. Nope, probably not. Probably something you're doing. But in this case, it's not something you're doing, it's something in the code that you were handed. Yeah. So did you have to fix it yourself in 40? Okay, yeah. So in CSI 40, then yeah, I think there was a note like figure out why it's crashing on in the San Joaquin map. Okay. So so how do we do that? How do we go about figuring out where it's crashing? Okay, I've already told you the answer, but how do we go about figuring it out? All right, so this Makefile here is compiling with debugging turned on. Okay, so we can go gdb a.out. Oops, quit. gdb a.out korea.dat. And we'll hit run, enter the starting row, 40. It didn't crash on that one. How do you pass command line parameters in GDB?
You have to do it when you type run.
Yeah. There we go. Okay, so program received, sig abort, aborted. Inside of raise.c line 50, backtrace. Okay, and this is why I've been trying to teach you guys these tools, because you need to be able to figure out where you crashed. And a lot of students were struggling with this. It's like, you know, this is why I'm trying to teach you, because this is a skill you will use all the time. And so one approach you could take is just see out all the things, just put see out statements all throughout your code and find out which line it's crashing on. You know, that's one approach. It's not a good approach when you have a lot of lines of code, because in this case, it's not your code that's crashing, right? And so a debugger is faster in this case. Okay. And if we go back to here, up 10 will take us up to frame 10. So basically, where did we crash? We crashed on main.cc, line 50, which called a function called getImage, and we crashed on line 112 inside of getImage. And that called the color.h code, which called setValue, which called setRed, which called setChannel, which threw. Okay? So this code is crashing inside of the bridges code. Inside of bridges, data structure, color, set channel, it's crashing. And the rest of this is just the exception handler. Okay. But none of this is actually interesting. What's interesting is where we went wrong. Our code, where we went wrong. Not the library code, where we went wrong. And so I went up, do you guys see this? Up 10. So I went up to frame 10 because there's 10 stack frames, 12 stack frames, right? This was called by this, which 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 was called by this. And so I went up to 10, get image. And I could like print the value of gray, and it's been optimized out. Great, cool. Let's turn off the optimizer. Crash. Raise is throwing an exception. Is the server just gonna? Okay. Make clean, make Makefile. So that I don't know if I'm using it in this one, but you can selectively include and exclude code from a .cc file. For example, I could say hashtag ifdef windows, have some call to some Windows thing that creates a window, else if else elif Linux, do a Linux function call that creates a window, or if I don't have any Windows Manager at all, else do some sort of incursus thing, endif. And then what you can do is say in your Makefile, -D will define something. So you can -D Linux, and then it would pick this line of code instead of that line of code. So you can selectively include and exclude things depending on your architecture or based on any number of other things. I don't know if we have Makefile actually used here. Yeah, I don't think it's actually used. But one of the ways, so you remember the static assert here? I don't allow you guys to just compile the code out the gate because I want you to put your name and API key in first. One way that I've done that before is I've just said if in def, if not defined, Makefile, cout, compile this code with make, not with G++. Or, yeah, that's fine. And then static assert. Actually, let's do this. Static assert false, won't compile. Endif. So this is part of what's called the C preprocessor. And so if it is compiled without -D Makefile defined, it won't compile. I can definitely 100% with no problem whatsoever understand why that's useful. For this thing here, because Linux and Windows are different. Linux has some system calls, Windows has some system calls. They do the same thing, but they have different names. Right? So like maybe on Linux you call write, and on Windows you call Windows write. I don't know, I'm just making up names. And so if you want your code to run on both Windows and on Linux, then you have a Windows section of the code and a Linux section of the code. And in your Makefile, you just -D Linux and it'll compile for Linux. That's how you can handle different systems, sure. Yeah. Because code won't compile if they don't exist, right? If I tried compiling this right now, this doesn't exist. See? Notice how it didn't say anything about the other things, right? It's because I didn't define Windows, I didn't define Linux, and so that is what gets included there. It literally cuts that out of the source code. This does not even appear in the source code. The preprocessor cuts it out prior to the C++ compiler seeing it. And so you can literally insert and delete different chunks of code from your code using the preprocessor. So, yeah, that gets used a lot. That's pretty neat, says Hazelton. Cool. Windows, yeah, which was the thing for a while. So that, and yeah, so there's if def, if in def, if not defined Makefile. And so if I just tried compiling this code manually like this, then it will not compile. So and that's a trick that I use to teach my CSI 41 students to use make on these projects. And so just in the Makefile itself, I define Makefile, and then it'll compile. Make clean, make. Can it be used for things besides the system you're running on? You can use it for anything. You could have different versions of your code. You know, if you run Vim Tutor, you know, Vim Tutor is Vim, right? But maybe compiled differently. Yeah, you can use it for anything. It's very, very open-ended and flexible. You can have a different version of your game that's in hard mode, you know. You can use it as an optimization technique rather than having an if statement. Like let's say that so you got a vector events named vec, and you're used to doing this, right? Vec.at 5 equals 42. You guys all with me? You guys all know what that is? So .at is slower than square brackets, right? You do vec square bracket 5 equals 42. This is faster. Faster and unsafe. Slow and safe. Okay. Very common trade-off in computer science. Do you do bounds checking? All right. And so what you can do is say if def debug else and if. Very common. Very, very common in computer science to have either a debug flag or a release flag, or both. And then when you're writing your code, you compile your code with maybe debug, like prints out extra things like cout, printing vec5, maybe when you compile with debug mode on, it prints informational things, and then maybe you do like elif release. So when you turn on release mode, you don't bounds check anymore, you want your speed. And if neither of those is defined, then you just do a vec.at 5 equals 42, right? And so that, and so if you compile the code with -d debug on, it's going to be printing things out, and you can sit there and look at your code as it's running and stuff like that. If you compile it with release mode on, then it turns off all the bounds checks, and it goes fast and unsafe, and by that point, you're probably confident it's working. And if neither of them are defined, it just uses .at by default. You guys understand? That's a very common thing, to have either debug flag or a release flag. And so release flags turn off all the asserts, they turn off, yeah. So we define things like debug and release at the top of the file. Yeah, you could do that. So you could say #define debug, and that'll turn on debugging. Or you can do #define log x to be x. You can write log this. And so this is a preprocessor macro. So it's a function. It's a function that runs inside of the preprocessor. And so what that means is anytime you see preprocessor, anytime you see the function, it's not really a function, it's preprocessor. Anytime you see the function log passing in x can be anything, it's not typed, then it replaces it with x. So what does that do? It just replaces this with cout, printing vec.at 5. Okay. Now if you ever want to turn off your logging messages, you do that. Then all of your cout statements turn off. So if you have a bunch of cout statements, you're logging your code, you want to find out what happens, you turn it on, everything's printing. After it works and you're tired of being spammed, you turn it off. And you can do that on a per file basis, right? So you can turn on logging and not logging on individual files. That's very common as well. Yeah. Very useful stuff. And so you can either define it here like this, Ribera. You can either hashtag define debug here, in which it's turned on for the file, or you come into the Makefile and you say -d debug. And standard library classes will actually pay attention to that flag as well. So if you turn on -d debug, that will have code work differently. Here, right here in my the flags that I give to you guys, it turns on. It defines -d defines glib C++ debug. And what that does is it actually modifies the standard library. It modifies the standard library to turn on debug mode. So rather than crashing, if you pop off an empty stack, which it will print an error message instead. So, yeah. All right, so let's identify the problem here. So we did a make clean and a make, and then we're going to do gdb a.out, and then we're going to do a run create.dat, and I can load all this up because all of this is in the input buffer. So the -d in the Makefile defines whatever follows as a preprocessor constant. Yep. Okay, so so to answer your question, it looks the same to me. Oh yeah. Okay, so let's go up to, where do we crash? Wait, dang. See, let's get rid of all this stuff. Huh? Okay. Make clean, make gdb a.out, run create.dat. So when I'm typing all this stuff, it's going to the input buffer. So the operating system has a queue, and as you type things on the keyboard, like I typed BT, I didn't hit return. If I hit return now, then it will come out of the thing. A.out, create.dat, thread debugging, terminate called. Okay, so here we are. All right, so yeah, so as you're typing, if the program is not consuming the keystrokes because it's thinking it's compiling the code, then all of the keystrokes you type in just go into a buffer. And when the program is ready, it'll start reading the keystrokes out of it. So where were we? All right, get image. So we're going to go up to frame 10, and we're going to print the value of gray, and the value of gray is -1. Okay, that's our clue. This is how quickly you can identify a problem. Okay, so if your code's crashing, open it up in the debugger, run it till it crashes, backtrace to see where you were, and then go up to a frame that you think is interesting. Set red could be interesting because you're seeing that the red is being set to -1, green, red, blue, and green are being set to -1. But I'm going to go all the way up to our code, and I print out the value of gray, and I find out the value of gray is -1. Okay, and so the fix for this if gray is less than 0, gray is equal to 0. That's it. That's all you guys had to do. That's it. Bounce check. Okay. But that's not the hard part. The fix isn't the hard part. The hard part was figuring out why the code was crashing. Okay. And I wanted you guys to get experience doing that. All right, so anybody who has done the assignment but has not submitted on Canvas, please do so, because otherwise you're just going to get a 0 if you don't submit anything on Canvas. I'm not going to dig around through people's directories if you don't submit anything on Canvas. All right. Any other questions about the homework assignment? Better to submit what you have. Submit whatever you have. Yeah, submit whatever you have. Better than nothing. I'm not going to dig around through people's source code directories. Okay. But yeah, that skill of being able to quickly zoom in and find where a problem is, it's so important. It's so important in computer science, and that's why I was not helping you guys with it last time. I knew exactly what the problem was, and I told you guys, like, part of the problem is in bridges, right? They assumed there would not be a negative elevation, right? So if you're in Colorado, it's a valid assumption, right? But when you get to any areas that have ocean in it, then it will crash. So our next homework assignment is going to be more fun, I think. It's going to be more fun. We're going to be doing image processing in C-Sci 45. You have to recompile every time to change your project ID. Yeah. What you could do is just see out what project ID would you like, and then just see in it. Or make it a command line parameter. Do you guys know how to use command line parameters? Let's probably go over that. You guys are old enough now to know about that. And do you guys understand the lerping concept of a lerping? It's used all the time. C++ 20 has a lerp function. So you lerp between A and B, and you pass in a number from 0 to 1. If you pass in 0, you get A. If you pass in 1, you get B. If you pass in a number in between, it will linearly interpolate between the two of them. Okay. So very common bit of algebra that they finally added a function for. So it's cool. Midpoint, that's cool. That's something new. All right, so if you wanted to not have to recompile your code, which is annoying because it takes a while to compile, right? So when you run a program, main is the interface between the operating system and your code, right? This is the interface point. We talked before about main returning int, right? You guys remember this? Why we return an int? Right? Yes? How that gets passed back to the operating system. Cool. This is what the operating system passes to you. So the operating system passes to you two things. The first is the arg count, which is a number. It's how many arguments are passed to your function. And the second one is an array of strings. And so a string in C, and this is kind of annoying to me that they've never built an overload for strings. You have to use the C style way of doing it. So a char star is a string in C++, and a char star star is an array of strings. And so if you grab, if you were to, for example, see out arg v square bracket 0, this would output the first string passed to the function. Now, what's interesting here is that the name of the executable is actually the first argument. So there's always going to be an argv 0. I'm not going to go out of bounds here by doing this. You'll see that when I run it, it will print a.out because that's the name of the executable. So if you ever want to know what the name of your executable is, because normally it's not a.out. Like the way that I do things is not here. You see that? Normally people name their executable Sorry, the blue microphone has a problem with it that if you wiggle the power cable, the mic will cut off. Sorry about that. So, how much did you guys not hear? $10 seconds? Okay. So the two parameters, the first parameter is how many arguments are passed to your program, argc. There are argc parameters passed to your program. And then the argument vector is what it's called. For int I equals 0, I is less than argc plus plus. Cout argv type nethack. Okay, that's fine. Nethack hacked my computer. And so the name of the executable is the first parameter. So there's one parameter passed to your program, and a.out is, so it actually passes the name of the executable. And the reason for that is because normal people name their executables. I name everything a.out because that way I don't have to guess what you guys name your executables. The autograder doesn't have to guess. We just always use a.out. It's the default name for an executable. In reality, though, you would give it a name. Okay, so if we run the program, if we run a.out, pass, let's actually rename a.out. Let's move a.out to be bridges mountains, like a proper executable. And if we run bridges mountains, you'll see the parameter passed into the program is bridges mountains. The name of the executable is the first parameter. Okay, but then if I say bridges mountains Korea.dat, you will see that there are two parameters passed to your program. Bridges mountains and bridges mountains and Korea.dat. And if I say bridges mountains A, B, C, D, E, F, G, you'll see that there are 8 parameters passed to your program. The name of the executable followed by A, B, C, D, E, F, G. Okay? Which of course causes a crash. Because we're trying to read a map that doesn't exist, I think. And so, yes. This is called so you guys are actually getting to learn lots of useful stuff today. Preprocessor directives, very useful stuff. Argument, parameter, passing parameters by an argument. I normally teach that in CSI 41. I think I didn't last time, so that's probably a little bit new for you guys as well. Okay, you guys understand? And so if you wanted to dynamically choose a project ID, then just take in another argument. You could say, for example, if argc is less than 3 usage, this is a very common thing that you'll see right at the very top of a program. If your program requires 3 arguments, the name of the executable, the map, and the project ID, that's 3 things, then you say if the number of arguments is less than 3, usage. And usage would be something like a function that says, to run this program, you type in a.out and map name and project ID. For example, a.out Korea.dat 9001. Okay. And so you'll see a function named usage in a lot of programs. And basically, if you don't type in enough parameters, if it's expecting a parameter, then it'll call usage, and then usage will exit. Yep. I think you guys like Dolio was saying, I think you guys saw why improving compile times is something we care about. So if you run the program now, it says to run this program, type in edit map name, project ID. So if I type in A and just, something like that, it still doesn't work. So I have to type in a.out, or it doesn't have to be create, Colorado, and then it'll run. Okay. You guys understand? Does that make sense? So like, here's my collect homework script. This is what's used to auto-grade your code. And yeah. And so you can see right here in shell scripting, I do the same thing. This is the number of command line parameters. It's a shell variable that holds how many command line parameters are passed. And so if the number of command line parameters passed was less than 2, then it will say usage and quit. So you'll see this kind of thing done all the time. And so that's the interface between the operating system and a program, and the program returns an integer back. Okay. Right. So our next homework assignment is going to be doing image processing. And so one of the reasons why I wanted to do bridges, mountains first with you guys is because it shows you guys how to render an image on bridges. So we're going to do another one of these with bridges. This time you are going to be loading a picture from disk. You're going to be applying a Photoshop filter to it and then rendering it inside of bridges. And there's going to be 2 different ways of running points for this, 3 different ways, I guess. First is correctness. So you're going to have to implement a Sepia filter. Okay. Do you guys know what Sepia filters are? Go away. So that's a Sepia filter. So it's that kind of brown look that a lot of old photos had. And so if you have you ever seen like old photographs? A lot of them have that kind of brown kind of look to them. So it's like a brown grayscale kind of. Brown scale, yeah, exactly. And so there's an algorithm that will do this. Basically, for every pixel, you take the red value, the green value, and the blue value, and you like blend them together. There's a certain magical numbers that will turn it into a brown for you, brown grayscale for you. And so that's what you guys need to do for the next homework assignment. So that's one thing, be able to do that. Second thing is you're going to have to make your own filter. And you will gain extra credit points based on the difficulty and creativity of your filter you make. So there's been all sorts of cool filters that students have made over the past couple of years that I've been doing this. Google Drive. There we go. So here is the image processing assignment from last semester. This is in CSI 40. It's a CSI 40 assignment. And so here's the, go away, pop-up windows. Here's their original, modified, modified, original, modified, modified, and then modified. Ori in the Blind Forest, Corrente, yeah, and then with a grayscale chunk out of the middle of it, and then that's a neat look. So they have like a couple different filters running. This is actually grayscale. This is washed out. That's grayscale. Could be Valheim. Sea of Thieves, more like. But. So you can see it's an opportunity for you to exercise your. This is a sepia toning right here. Actually, it's an opportunity to exercise your creativity. Definitely scanned in, so you got a mountain, heather or something. And then they inverted the colors, and they did that. Okay. So what you're going to do is, so there's 3 parts to the assignment. The first one, you have to do sepia toning just to show me you can do it. Second is creativity, make your own filter, show your creativity off. You're going to be judged purely on artistic merits, difficulty, and beauty. Okay. And the third thing, you can pick any image you want, make any image filter you want. It's fine. But don't do something simple like grayscale or something boring like that. It's kind of too lame to get points. And the third thing is speed. So you're going to be timed on how quickly you can sepia tone a 4K image. Okay. You lack artistic skills. These custom filters are extra credit. Nope. It's required. It's required. You have to be creative, Mr. Singh. Mm-hmm. So, well, I'll show you guys how images work in a second. So we got some Evangelion thing going on here. It's a pretty nice look. Yeah. So students have done really good jobs in the past on this assignment. Sepia will be the only one graded on time. That is correct. Yeah, because otherwise people would just do a simple filter. You know what I mean? And so the 3 things you're going to be graded on are: 1, make a sepia filter. 2, make your own, graded on creative and difficulty. And 3, speed of sepia. Okay. That is, you can work on this with a partner if you'd like. Okay. If you work on it with a partner, then you will make 2 artistic filters. So for this one, you'll have 2. You do 1 and your partner does 1. Okay. You mean like runtime, right? No, not speed run after you deploy it. Yeah. Runtime, running speed. Runtime speed of sepia. Okay. And I will give you C++ code that does sepia toning. Okay. So you don't have to figure that out. Right? There's magic numbers that make it sepia tone. You don't have to worry about that. I'm giving that to you. You have to write it in assembly. Okay. You can sepia filter in assembly. Okay. Reverse engineer sepia. Yeah, I mean, I guess you just. Yeah, I'm giving it to you. But the challenge is getting it to run quickly, because this is a Raspberry Pi. Raspberry Pis are not known for their processing power, and so the easiest way of doing it's not the fastest way of doing it. And today's lecture will show you guys there may be a faster way of doing it. Okay, so that's an image. I'll give you guys till next Friday. I'll give you guys 9 days to do this one. All right. make your own filter. Graded on creativity, beauty, and difficulty. If you have a partner, you must submit to and okay, submit a link to the Bridges website where your image can be viewed, both the original and modified versions. So you will need to use a different project number for each one. Thus, you'll need to use a different project number for each one. Maybe now is the time to learn how to read from the command line parameter vector argv to easily pick a new project number without needing to recompile each time. Or just CN it. You can use CN, that's fine too. This isn't going to be auto-graded. Okay, so there you go. This will be worth 10 points per new project. Online, yep. A lot of attempts. Plagiarism is a group assignment. New group category. This will be called image groups. Allow self sign up. Create 20 groups now. Groups limited to 2 members. There you go. So you guys, if you want to sign up for a group, you talk to your buddies in the class. If you don't have a buddy, just say, hey, I'm looking for a partner. You can do this either individually or in a group. If you do it in a group, you need to submit to custom filters. Use the people groups tab in Canvas to pick a group. Okay. So if you go to the people section, go to groups, you'll see that there's one called image groups now. And just sign up for the same group as your buddy. Okay, and this will be due next Friday at 12. There you go. So it's a fun assignment. Render it using Bridges. I would copy and paste the code from the current one. Right? You know, this code has remove this code has this color grid and this get image function. So that's what is making a image. Okay. So that's how you render an image in Bridges. Okay. So just use that, and I'll push out the assignment with the sample code and all that in a little bit. It's 1 o'clock now, so I want to actually get to the PowerPoint presentation. And so today we're going to be learning about something called SIMD. And is this relevant to your image processing assignment? Yeah, it is. It's very relevant. Okay. This is how you will win at Sepia speed. All right, so midterm, homework, whatever. Okay, so last time we were talking a little bit about weighing computers, right? Which is early 70s. They were a competitor to DEC, really. Their VAX machines were competitors for IBM, and then Wayne came in and came out with a cheap $45,000 in modern terms computer. $8,000 per K of RAM. Yeah. But we're going to go back into history again, and we're going to learn about the craze. So, back in the day, there's this guy named Seymour Cray, and the dude was like this brilliant computer engineer, right? And so he made some of the fastest computers in the world for a good, 15 years or so. His company like dominated the supercomputer market for years. And so his philosophy was, would you rather have 2 oxen pulling a plow or 1,000 chickens? Right? His approach was that rather than focusing on just a single CPU or having 2 CPUs that were big and strong, what you do is you have a CPU that can do a lot of work at the same time. In other words, massively parallel processors. So a processor that could do like, maybe 1,000 multiplies all at the same time. Do you guys see how that's useful? Like, so if a CPU could do 1,000 multiplies at a time in one cycle, like, do you guys understand how that would be like kind of neat, kind of useful? So like a GPU, yeah, it's still around. So 30 years before GPU compute, yeah, yep. So this was actually implemented in Intel in the 90s, but very small. Intel in the 90s it would do 4 multiplies at a time. So they had in the 70s they had 8 registers in their computer at a time when Intel didn't even exist yet. And Intel, when it did come out, had 4 registers, and the 4 registers were just, they weren't even regular integers back then. I think they were either 8 or 16 bits. I don't even know how terrible it was back in the 8088 days. But he had 64 times 64-bit registers. So in other words, every register held enough room for 64 64-bit numbers. Do you understand how big a register that is? Like our Raspberry Pis, the registers are 32 bits. You know what I mean? And when we learn about SIMD and the Raspberry Pi, you learn we have some bigger ones as well. But yeah, this is the 1970s. And 64 times 64 is 4,000 bits. Right? That is a big-ass register. Okay? So it was capable of doing 64 multiplies and 64 adds in the amount of time it took to multiply just 2 integers. So it's not like a one-to-one comparison with our modern architectures, but let's say that on the Raspberry Pi, you could multiply A times B, mul. It takes 4 cycles or whatever. It could do 64 multiplies and 64 adds on 64-bit numbers in the same amount of time that it would just take to multiply 3 times 3. You guys see why this was a fast machine? What do you guys think? The trouble was, how do you get enough numbers to multiply it, right? And so, these things weren't used for like running Crisis or something like that. I see why Jurassic Park sought them out. Yeah. It wasn't used for running Crisis or games or things like that, because typically in a game you don't need to do that many multiplies all at the same time. But if you're doing linear algebra, which guess what? There's a lot of need for linear algebra. If you guys haven't taken linear algebra yet, I recommend you take linear algebra. It's a great class, very useful. If you're doing a matrix, you're going to do a ton of multiplies and a ton of adds. And so this thing was really optimized for doing linear algebra computations. So the military, for example, if you want to, this is what my uncle did, by the way. My uncle he worked for the Air Force doing Air Force logistics. And so the Air Force would have a number of requests. Hey, we've got a squad of guys here in Poland and they need to be transported to France. We've got a couple tanks that are in Turkey that need to go to Kuwait. We've got a bunch of oil barrels in Kuwait that need to go to... And so what they would do is they would take all of these requests and then they would have all of their transport planes. And some transport planes could carry tanks, some couldn't. Some could carry people, some couldn't. Well, probably you could pack people into anything, but some could carry oil and some couldn't, you know. And so you have all these different constraints. You have all these different planes, and they're located in different places around the world, and some need to go down for maintenance, and some are ready, and some have pilots, and the pilots have to have rest cycles. You know, after you land a flight, you have to give the pilot 8 hours off so they can rest. There's all of these crazy constraints. And what they did is they would convert all of that into a linear algebra solution, solver, basically. And then they would run the linear algebra solver on it, and it would spit out orders. This plane needs to fly to Poland, wait a day, pick up the people, fly to France, wait a day, go to England, go here. And then and you're doing that for all 500 cargo planes that are available at any one time. Crazy, crazy difficult program to write. And so this program... Nobody understood it, by the way. Nobody understood it. It was written back in the 1970s, and all the people that had worked on it since then had improved it and worked on it. But by the time the 90s rolled around, when he was working on it, nobody understood it. Like, nobody knew what all the code was doing. It was written in Fortran. And there were parts of the code that just nobody would touch because nobody understood it, but it worked, so they just left it alone. And they were like tech priests, you know, they were just worshiping the machine and just kind of tinkering with it and keeping it working. We don't know why it works, but when we twist this knob here, it works, so we're just going to keep doing that. And it was just 5 guys that maintained this program. And they're all, you know, they were all in their, you know, late 50s and 60s at that point. They're all probably retired now. So who knows who's running it now. But at some point they would have to probably start hiring new people. And new people these days don't really know Fortran very well. And so, you know, it's kind of interesting, you know. I'm kind of curious what happened to that software. You know, I haven't heard any disaster stories coming out of the Air Force, so they probably figured it out. But linear algebra and graph theory coming together could be powerful. Yeah, that's right. The Shaolin style and the Wu-Tang Clan, if they came together, it could be incredibly dangerous. So, if you can keep the vectors loaded, you could do a lot of math very quickly, right? And so this is what the Cray 1 looked like. This was the 1970s, so of course everything had to be wood paneled. And on the inside there you can see the cables. And so this would be in a machine floor room. So like I talked about last time, you know, they'd have these elevated floors, and beneath the floors they run the power and the cooling and things like that. And so these things look cool. You could actually sit on them, I guess, if you wanted to. And that was one of the things that he optimized for. He actually hired what are they called? Industrial design people. That's probably not the right word. But he wanted his computers to look cool, so that when people went into a supercomputer center and saw it, they're like, "Oh, what's that? Oh, that's a Cray, a Cray," you know. And so, yeah, all of his machines looked very futuristic and sci-fi, and this is cool. Like even today, even though you can tell this is a product of the 70s, it still looks cool, you know. And so they'd run the cooling through here, and then this is all the different vector processors and things like that. So it ran at a whopping 20 megahertz. 20 megahertz. The Apple II at the time was at 1 megahertz. So it ran 20 times faster than an Apple. So, you know, that was probably part of the performance. And actually it's part of the reason why it was expensive, right? Because they had to use, I think it was like germanium something or other. They had to use a different process for making the CPUs that allowed a higher speed, but was also exponentially more expensive. So they had 2 CPUs. Each CPU could do 80 million floating point operations a second. So it could do 160 million floating point operations per second, which is pretty good, honestly. 8 megs of RAM, sold for $9 million. Okay. By contrast, an Apple II had a 1 megahertz CPU, so it was 20 times slower. 4K to 64K of RAM. And back then, like, a K of RAM was like, you know, expensive, right? See, in the Wang days, it was like what? It was like $4,000, $4,500 for a K of RAM. By the late 70s, it was probably down to about $1,000 per K of RAM. It was still pricey. Still pricey. And then by 1988, so 9 years after the introduction of the Apple II, they were up to a whopping 4 megahertz, so they had quadrupled in speed in 8 years or so. And the amount of RAM they had gone up by an order of magnitude or two, depending on, it's 64 times bigger. And they cost about $1,000. Okay. In dollars at the time. This is not inflation adjusted. So the Apple II had MOS 6502 classic CPU. This was what was used in the NES, the original Nintendo Entertainment System. There's a whole story about MOS that maybe I'll tell at some point. Pretty cool stuff. Had one general purpose register and 5 other registers for the stack pointer and the program counter and stuff like that. So it had one register to play with. Called the accumulator, because you would accumulate all of your math into it. And then you'd basically have to read and write to RAM all the time, so it was not fast. It would do 400,000 multiplications, or integers. 400,000, I think that M is a typo. Integer operations per second. So this thing was doing floats instead of ints, which is always harder. And so it was about 10, 100, 200 times faster, 400 times faster. So it's about 400 times faster, and it's doing floats, so it's probably even faster than that. So the Cray was awesome. And then you can see in just 5 years, their clock rate went up by a factor of 5. Their processing power, they had 4 CPUs instead of 2, and each CPU was doing almost 3 times the work. The amount of RAM went up exponentially. RAM started getting cheap in this time period. People figured out how to make RAM cheaply, and so RAM sizes went up a lot. At the time that the next generation of the Apple II came out, they had a max of a meg of RAM. A Cray had 512 times the amount of RAM of a personal computer, and cost substantially more. Right, so rather than $1,000, it cost $30 million, and had 2.4 billion instructions per cycle, per second. So by that point, it was 8,000 times faster than a PC, something like that. Okay. And then by comparison, a Raspberry Pi 2, which is 2 generations old at this point, does 500 million operations a second. So it was faster than a Cray 1. It was slower than a Cray XMP. So our current Raspberry Pi, I think, does like about 1 billion, something like that. So our current one is somewhere in the mid-80s as far as supercomputers go. What do you guys think about that? I mean, yeah, it does require less power. A Raspberry Pi draws, like a Pi 2, I think draws like a watt, 2 watts, something absolutely insignificant. Especially compared to this PC that I have here that functions as a space heater in wintertime. And I actually had to build a custom AC unit in my office here, because during the summertime it got so obscenely hot that I actually drilled a hole in my wall and put a space... I'll show you guys this. There's a space, or what's it called, split unit cooler that I had to put in here, because otherwise I'd have to run the AC for the entire house, which was ridiculously expensive, just to cool down this office. And so it was actually cheaper to put in a second AC unit than it was to pay power, and it delivers a lot more cold air here as well. The i9-7900X uses 140 watts, yeah, and the 3090s draw 350 watts of power. So you're talking, what was that, 400 watts just for your CPU and GPU, And a Pi 2 is just sitting pretty at like 2 watts. So the original Raspberry Pi was marketed as a $5 mid-90s PC. Yeah, I mean, we're comparing this with a Cray. But if you look at the contrast between a Pi and an Apple, the Apple II Classic, Oregon Trail, came out on that. It is what was that 1,000 times faster than an Apple II. So yeah, pretty good. It's pretty good. So here's the Cray XMP. What do you guys think of the look of that one? Do you like the original one better? Do you like this, the Cray one, or the XMP? Not a fan of the red. All right. Well, what about? Do I have another one on here? No. Evangelion. Really? Is that? I don't have a picture of a YMP. Who made this? Who made this presentation? Because the Cray YMP was the first one I saw. Cray YMP. That was what they had at the Supercomputer Center when I visited it, when I toured it for the first time. And that is a sexy beast right there. Look at that. That is a nice looking. That is a nice looking computer. See, the XMP is just it's like too red for me. I mean, it's cool. It's got this cool bridge and it's like this red velvet kind of thing. But the YMP, yeah, that is a cool looking machine. It's like something you'd see out of a video game. So, Gamer Red, right? Like if my machine looked like this, like my case, like I would have a case that looked like this. Like I used to hate all these RGB effects and transparent windows and things like that on the side of a case, and then after a while I just couldn't find anything that didn't have RGB effects in it. Like I'd just buy a fan and it would have an LED on it, and I'm like, what the hell, dude? And so I went from my machines for years just looked like this, beige box PC. Went from this, because I really didn't care what my computer looked like, to like I have one that has a glass on the side of it and glowing LED effects, and because I couldn't, I just gave in to the insanity, I guess. The Virtual Boy, yeah. So okay. So let's talk a little bit about Flynn's taxonomy. This is a thing that it's part of the vocab you need to know for computer science. And so it divides all computers into here's a graph. It divides all computers into 4 categories, and I'll go through what each of these are. But basically, the question is, do you have multiple instruction streams running at the same time? In other words, do you have multiple CPUs, multiple cores? If you have multiple cores, then it is multiple instruction. If you have a single core, single threaded processor, then it's a single instruction processor. And the other question is, when you run an instruction, does it run on one number at a time, or does it run on multiple numbers at a time? So for example, add R0, R1, R2, that would be a single data. It's writing to R0. If, however, you could do 4 multiplies at the same time, that would be multiple data. And so between these 2 questions, the 2 questions are, does it run multiple instruction streams at the same time, or is it single threaded? That's one question. The other question is, can it run on multiple data threads at the same time, or does it only run on one number at a time? Okay. So why would you build a PC if not to make it look pretty? Because I'm not impressing people here. Like I don't bring friends over, be like, hey, look at my PC. Although I guess I've done it now that I've got RGB effects everywhere. Like I bought a mouse pad. My mouse pad has RGB effects on it. My mouse glows different colors. Like, what the hell, dude? It's like I didn't even ask for it. It just comes with it. My keyboard, all of it's synced to Wallpaper Engine. So as my Wallpaper Engine changes, my keyboard changes colors. My mouse pad changes colors. We're living in a bizarre timeline, people. I've given into the dark side, more or less. Yeah, I just sort of embraced the stupidity of it. RGB gives more FPS. It's like putting stickers on your car to make it go faster. Okay, so yeah, and so basically how you answer these two questions controls which category of machine you have. Okay. It's kind of irrelevant today. Almost everything is MIMD these days, but let's go through it. So a old school CPU, like if you have an Arduino or something like that, I've got an Arduino over there. It would be very exciting to show you. It's just a chip. But an Arduino is a SISD, single instruction, single data. Single instruction, single data CPU. So basically it reads one instruction at a time, one assembly, one assembly, one assembly, runs it, runs it, runs it. It runs on one register at a time, right? Or it reads from two, writes to one, you know. Bloop, bloop, bloop. Basic, single threaded, boring CPU. And this is how CPUs used to be in the 90s, early 2000s, before we got multi-core computers and multiple CPU computers. You know, this was your basic CPU. It just runs one instruction at a time, and yeah. And then if you want to do multi-threading, what happens is the OS will take your process and pause it, swap it out, swap a new process in, run it for a little while, pause it, swap it out, swap in something else, run it, swap it out, swap it in. And if it swaps programs back and forth, it's like the illusions of animations, right? Where you have a picture of a horse and on a flip book and you flip the book really fast and the horse appears to be running, but it's actually just showing a lot of still images. That's how multi-threaded worked back in the day. Was the OS would just very quickly switch. It would switch Vim in and handle all your Vim keystrokes, then it would switch it out and run the operating system for a little while, and then it would switch back to Vim and handle your keystrokes, and then it'd switch to, you know, something else in the background and switch back, and as long as it switched back and forth fast enough, it would seem like you owned the CPU and it was responding to your keystrokes. And if you weren't typing anything, Vim would go idle, and so the CPU would detect that the OS would detect it was idle and put it on pause until you typed something, and then it would wake it up again and handle the keystrokes. And so you could have 40 people on a SISD CPU, and it would just juggle them. It would be like keeping 40 balls in the air at the same time. And if everybody started using it too much and it ran out of CPU power, then you would get H-top. We got 4 cores on here, so it's not SISD, but you would see just 1 core, and you'd see the thing pegged at 100%, and you'd see the load above 1. And so load means how many processes are waiting to run. And if that ever climbs above 1, that means at any given time, there is one process that needs to do work that can't do its work. And so as long as your load is below 1, that means the CPU is able to keep on top of it and keep all the balls juggling in the world, all the balls in the world juggling in the air. But if everybody starts running all of these like computationally intensive tasks, like average a big array and stuff like that, and all these people start running things, benchmarks and things like that, then the CPU starts crying. And the load will go from 0.35 right now to 1 to 2 to 10 to 30, meaning there's 30 people who have processes that need CPU time that can't get it. They're just waiting in line right now. And when they get to the front of the line, the CPU will run them for 20 milliseconds and then pause them and switch them out again. And so the CPU at that point is, you will notice the computer becomes very laggy at that point because it's trying to juggle everybody's tasks. You guys understand? Are you really a gamer if your PC doesn't blind onlookers? So do you guys understand how that works? How it kind of switches, pause, switch, pause, switch, and that's kind of how it pretends to work for multiple people. Okay, so that's your boring CPU, the SISD, single instruction, single data. SIMD is our topic for today, and this is what you're going to be using to get speed out of Sepia toning. Okay, so SIMD means that one instruction can do multiple multiplies at the same time, right? Just like what we had with the crave back here. You could do 64 multiplies and 64 adds with one instruction. Okay, so that is, if you could do one instruction, vector multiply add. If you could do one instruction that does multiple datas at the same time, that's SIMD. Single instruction, multiple data. Okay, and so the Raspberry Pi that we have has something called Neon, N-E-O-N, which is based on an older thing called VFP, vector float processor. A vector float processor, well, that's the Cray. They call these things vector registers. And so when ARM decided to do this, they're like, we will call our things vector registers as well. And so it's called VFP, vector floating point. Okay, so SIMD, for example, this is not exactly how it works, but think about it. If you could give a command, a single command that said, multiply all of the registers from 0 to 7 by 10, right? So take all the values from R0 to R7 and increase all their values by 10. That would be SIMD. Does that make sense to you guys? Doing multiple multiplies. Multiplies. So one command, one cycle, or 4 cycles in this case, to do 8 multiplies. SIMD does vector operations, yeah. I haven't taught you guys how to do it yet, so this is just more conceptual. This is not how, it's not how it actually works. So when you're doing linear algebra, you're going to do multiply and adds over and over again. Multiply, add, very common. And so if you're doing image processing, you're going to be doing multiplies and adds over and over again. And so if you could do, say, 4 of them at the same time, then you're going to get a 4 times speed increase. Okay? And so that's our topic for today, really, is SIMD. But let's go through the other 2 options. MISD is the least used of the 4 categories. MISD means you have multiple instructions running on the same data. Multiple instructions, single data, which is a weird concept. Imagine you've got 4 different CPUs, and they all take the same number in and multiply it by 12. Like, what's the point, right? You're just duplicating work. The only point for it really is to do fault tolerance. And so if you are making a rocket ship to Mars, you might have 3 CPUs, right? And so the 3 CPUs might do some computation, and at the end of the day go like, turn off the rocket, turn off the rocket, turn on the rocket. What? These 2 outvote the 3rd one. Okay? So if your CPU gets hit by a cosmic ray, which happens in outer space, there's not as much protection against cosmic rays, it will flip a bit. And you don't want bits flipped when it comes to things like turning on rockets and like deploying parachutes and things like that. You really want them to happen when they're supposed to happen, and you don't want them to happen when they shouldn't happen. Okay? So the last Mars rover, I don't know about the current one. The current one, I think, has the CPU from like 20 years ago in it. I think it's like the iMac CPU or something like that, or the G3 iMac. But the one prior to it, I actually watched a talk by GPL on it. The CPU is actually made out of sapphire, which is pretty cool. Like, it's a gemstone CPU. Instead of silicon, it's made out of sapphire, which is pretty damn cool. And the CPU costs like $300,000 or something like that, because it's a gemstone they etch. And because it's made out of sapphire, like, it's resistant to cosmic rays and things like that. So it's hardened. It's called rad hard, radiation hardened. And so anything that goes into satellites are way more expensive because they have to rad harden them, right? Or they have to buy rad hard CPUs. And so, because they get bombarded by radiation all the time. And if you have your CPU vulnerable to radiation, the cosmic rays, and it's like, initiate abort sequence, and the satellite flings itself out of orbit, that's a lot more expensive than buying an expensive CPU, you know what I mean? Because you've gone to all the effort of putting a communication satellite into orbit, all the very expensive things on that, and the things like, let's do a termination burn, and it crashes itself. You don't want to do that. You don't want to do that. So they spend a lot of time thinking about these problems in outer space. And so you might have 3 CPUs that are all rad hardened, and 2 of them will outvote a 3rd one. And if the 3rd one disagrees, then it'll probably display like an error message like, hey, we can't trust Ribera over there. He's voting against us. I don't know what's going on. I think we need to. So, yeah, and so this is basically the only use for MISD. So you're doing redundant work to make sure you don't make a mistake. And so, yeah, Ribera is sus, right? And so that philosophy is actually used in a lot of circumstances. If you have an airplane, you guys know how there's like the flaps that come out the back of the airplane, or you got your elevators and the ailerons and things like that, all the wiggly bits of a plane. If you were to deploy flaps when you're hypersonic, your plane will explode. In fact, that happened to a Russian test pilot. They were test piloting this cool plane where the wing could extend like a bird's wings, kind of. It was really neat. And there was no safety measure on deploying the flaps, and he brushed the button to deploy flaps at Mach 2, and his plane, he went from being an alive person to atoms within a microsecond or something, right? That was it. You don't want to deploy flaps when you don't want to deploy flaps. You don't want to turn left when you're trying to go straight, you know what I mean? And so all the wiggly bits on a plane are designed with fault tolerance in mind. Not that Russian plane, apparently. There should have been some sort of software that said, no. And maybe allow the pilot to override that in case the airspeed indicator is wrong or something. But yeah, just if you brush a button and it deploys flaps and you die, that's probably bad design. So on an airplane, what happens is you'll have like 3 different pistons. And it's set up so that none of the pistons can actually extend the flaps or wiggle the aileron or elevator by itself. You need 2 of them to activate in order to extend. And if the third one doesn't extend, the 2 of them are strong enough to overpower the third one not wanting to extend. And so it's a physical voting system, right? Where you have a malfunction in a hydraulic line or something like that. It doesn't matter if 2 of them turn on and the third one's like, no, I'm not turning on, man. The 2 of them will outvote the third one. And airplanes are extremely fault tolerant. My professor for fault tolerant systems was really big on aeronautics because airplanes have more thought put into not crashing than almost anything else. The space shuttle would be another example of fault tolerant systems. The amount of time they put into not having a space shuttle crash was, ironically, because it did crash occasionally. It's a rough, it's a tough thing to do. But the space shuttle, they put an enormous amount of effort into making it not crash. The amount of code reviews you had to do, like if you submitted a patch for the space shuttle's program, like there was like 7 levels of code reviews and things like that, where people would go over every line of code you wrote with a fine-tooth comb, thinking about every possible way that it could crash. Like for the last homework assignment. What if that float is a negative? Oh, I didn't think of that. Right? And they would have a team of engineers and software engineers, not just software engineers, but people from every discipline looking at the source code line by line, and they would go over it with a fine-tooth comb. The Mars rover as well, they have you can read JPL's code recommendations. They do everything in C, not C++, because they don't trust C++. There's hidden functions that run, hidden constructors, hidden destructors, and they've got all these different rules for C, don't do any dynamic memory allocations after launch, all this kind of stuff to make their code not crash and be reliable. They want it guaranteed to run correctly. So, yeah, dumb question. It's not a dumb question. Is multi-threading essentially enabling multiple data streams? Yes. So that is bringing us to our final quadrant, which is modern CPUs. So modern CPUs have multiple cores. Each core oftentimes will do hyper-threading, which means it pretends to be another core. Remember how last time we were talking about pipeline stalls? Do you guys remember that? How especially if you're doing a load, sometimes there's just an unavoidable pipeline stall, right? If you're going to be loading data from RAM and then doing math on it, there's nothing you can't out of order your way around that, right? Because you're just loading things from RAM. You guys remember that from last time? Hopefully. So what happens is Dean Tolson, one of my architecture professor at UCSD, he was one of the guys that invented hyperthreading. And hyperthreading is the notion that one CPU core will appear to be 2 CPU cores. And the reason why we do that is because the operating system will schedule different processes to run at the same time on different cores. And so what happens is that if, let's say, process 1 is doing all these loads and it's just going to hang out for a while, then the other thread, which is running Microsoft Word, let's say, all those gaps in the pipeline could be filled in with another program. And so it's actually running two programs out at the same time, because that one core is appearing to be two different cores. And so it could be running the code from one core and running code from another core, and they both go into the pipeline at the same time, and they're just tagged with, is this core 1's instruction or is it core 0's instruction? You know, is this core 1's register 0, is it core 7's register 0? You guys understand? And so by doing that, then if you have all these bubbles in the pipeline, you can actually increase the utilization of your pipeline. So a thread is a fraction of a CPU. If you're talking about hyperthreading, yeah. So hyperthreading is it's two logical cores. They appear to be cores to the operating system, but what happens is that in reality, the two of them share a physical core. They're actually one CPU. And we do that because most programs will have stalls in the pipeline, and if you run two programs at the same time on the same core, then it fills in the gaps in the pipeline very nicely. But it's still not as efficient, because what if the pipeline's full? In that case, it's better to schedule. It's better for the CPU to schedule something on a different physical core rather than on a different logical core. So it's good to have 10 physical cores, and after all 10 of those have been assigned programs, then you can assign things into the matching logical cores as well. So that's what you're looking at here. You got core 0, core 1, right? Okay. So that is called MIMD, multiple instruction, multiple data. Most modern CPUs these days, all Intel CPUs these days, more or less, have multiple cores, and they can run multiple programs at the same time. So you saw my graph there. It was running Discord, and it was running PowerPoint, and it's running OSD all at the same time, and they're actually running at the same time. It's not swapping between them necessarily. It could be, who knows, but there's actually multiple cores that are all multiple instructions running on different sets of data all at the same time. And so hyperthreading is when a CPU pretends to be two CPUs or more. You could do four-way hyperthreading as well. Is there a difference between multithreading and hyperthreading? Yes. Multithreading means you, as the software engineer, are writing a program that has multiple threads. So if you write a multi-threaded program, then you write a program that has multiple threads of execution in it. And you can do that really easily, actually. It's surprisingly easy to do in C++. So there's the thread library. C++.com. Why do you always come up first? Yeah, so if you have a function named foo and a function named bar, Ribera, if you want them to run in parallel with each other, in other words, running at the same time, not sequentially, then you say std thread foo, and you give it a name first. Std thread bar, passing in a parameter to it, called second, and then they will run in parallel. That's how easy it is to do a multi-threaded program. If these two things don't depend on each other, then hell yeah, do that. And what will happen is the operating system will be like, oh, you've got two threads now. We got a 4-core Raspberry Pi. Put one on the first thread. Put thread 1 on the first CPU. Put thread 2 on the second CPU. You know, this might be useful for your Sepia tuning assignment. Who knows? And then you just do a join to wait for them to finish, and so that will wait. This will return once foo finishes. That will return when bar finishes. That's it. So you can have foo do the top left corner, bar do the top right corner, was do the other corner. So you can split it up that way. Okay. Can the optimizer do this by itself? So the answer is no, but also yes, and it will do SIMD. So there is something called -f tree optimize, which will do SIMD. So that vector processor stuff, the C++ CPU, the C++ optimizer, compiler / optimizer, will detect when you have a loop that could be parallelized, and it will issue SIMD instructions that we're going to learn about in just a second. So this is Flynn's taxonomy. Okay. And more or less everything is MIMD these days. So it's kind of not really super important. You know them. However, knowing the term SIMD, we don't use these three terms because everything is basically MIMD these days, but we will use the word SIMD. And SIMD is our topic for today with Neon. SSE is the Intel version of it. GPUs are SIMD. The Cray vector stuff is SIMD. What that means is you give one multiply that can do multiple multiplies. So it's much faster. Okay, so know that term, SIMD. That's something you will hear programmers is talking about. Hey, I modified my program to use SIMD. Oh, cool. What speed up did you get? Oh, I got a 3 times speed up. Wow, that's good. Yeah. That's part of your vocab as a programmer. Stood thread minus c++.com. Yeah, thanks. But that's not our lecture for today. So all that Cray vector processing stuff, it's now just everywhere. So in Intel, they added SSE, which was in the late 90s, I think. 99, yeah, cool. And so it's the same idea, where you can do 4 multiplies at the same time. Why 4? Because in 3D graphics, you typically are doing a 4x4 matrix multiply. So in video games, in any sort of 3D rendering stuff, all the time you are doing a 4x4 matrix, and that 4x4 matrix is either going to get multiplied by another 4x4 matrix, or it's going to be multiplied by a 4x1 vector. And to multiply a 4x4 matrix by a 4x1 vector, you take the vector, turn it sideways, multiply down, add across. It's a bunch of multiplies, bunch of adds, and that's what it's optimized for. So it does 4 at a time for that reason. On ARM, it's called Neon. And you also see terms like MPE and VFP. We're going to learn Neon. Okay. So Neon Genesis Evangelion is, of course, one of the best animes of all time. And what it allows you to do is it allows you to drastically speed up your code. It's also how you can do floating point math. We haven't done any floating point math in this class, right? Nope. Now you're going to learn. Okay. And so Evangelion is messed up. Oh, come on. What do you mean messed up? It's just a humorous anime about a boy, and, he's got a penguin, and he pilots giant robots. It's just a stupid giant robot anime. Okay, so he pilots his mom. Spoilers, huh? And that's also his mom. Hey. All right, so in Neon, we have what are called quad registers. There's also double registers. There's also single word registers. But if you guys remember the terminology, a word is 32 bits, right? In ARM32. A word is 32 bits. And then you can have a double word, which is 64 bits. And if you use Neon, there is a quad word, which is 128 bits. Yep. And so there are registers. There are registers called Q0 and Q1. These are quad word registers. They're 128 bits wide. And they're only found on ARM processors that have Neon on them, which is not all of them, but our Raspberry Pis do, so cool. And so what you can do is you can actually treat one of these 128-bit registers. This works just like how the Cray worked. So you can treat the 128 bits as if they were 4 different registers. So one quad word register can actually work as if it was 4 different ints. And so you can say, like, multiply all of them by 10. And then they'll all multiply by 10. And they don't overflow into each other. You would think the bits would, like, overflow. Nope. With Neon, it puts up a little dividing wall between each of the 4 different ints. And if you multiply it by a big number, it won't overflow into the next channel. Oh, or you can treat it as 8 different 16-bit registers. Or you can treat it as 16 different chars. So if you have 128 bits, you can actually divide this into 16 different chars. And for your image processing thing, guess what? Every red, green, and blue value is a char. It's a value from 0 to 255. And so by doing Neon, you can actually do 16 multiplies or 16 adds all at the same time. It would not wrap. It would just it's just like when you overflow an integer. So Yeah, and so if you had a quad word loaded with 16 different chars in it, you could add 10 to each of them, and it would do that in one operation, which is really cool. So you can get 16 times the performance by using Neon. Okay. And these registers aren't, they're separate. They're totally separate from the R registers that you've been working with. So that it actually gives you more registers to play with, which is nice. Typically for control, for doing things like for loops and things like that, I use the R registers. And then for doing data processing, I put things into quad registers. Okay. So let's look at some code. So this is what it looks like. So you've got 16 different quad registers, Q0 through Q15. These things are also the double registers, and they're also the single registers. So so if you were, let's say that you set D0 to be 0, and then you set quad 0 to be 100 million, whatever. What actually happens is that quad 0 and D0 are actually the same register. So if you write to register D0, that's going to write to the upper half of Q0. And if you write to D1, that's going to write to the lower half of Q0. So advice, just use the quad registers. That's my advice to you guys. If you mix and match, if you use some S registers, see every 2 S registers is a D register. So S0 and S1 together form D0, and D0 and D1 together form Q0. And so if you were to write to like S2, that would actually modify this part of Q0. So my advice to you guys is just to ignore the S and the D registers for now, and just use Q. Okay? You guys understand? Like, it's the same chunk of memory. So you have the same register bank. It's just named different ways. You guys see that? So if you were to read and write to D14, that would be reading and writing to the upper half of Q7. Or if you understand this, then just use different ones. So like maybe use Q0 and Q1, and then D14 and D15. That would be fine. That would be fine. Do you guys understand that? Q registers are accessed the same way as R registers, just with Q. Nope. Different instructions. Neon is its own instruction set. So here's the result of my sepia toning. So I showed you guys this meme last time, I think. So do you guys understand this a little better now? So you have Spider-Man Q0 pointing at D1, pointing at D0, and they're pointing at Q0. Technically, D1 and D0 are not the same thing. These are 2 different registers. But D1 and D0 are the same thing as Q0. You guys understand? These 2 guys put together is the same register as Q0. Replace D1 with S0. Yeah, that'd be correct. Yeah, if you replaced D0 with S0, then that Spider-Man meme would work. Okay, so what you do when you do anything with Neon is there is a new suffix you add. All of the Neon instructions, by the way, are going to start with a V because it stands for vector processor. And so you're going to do a vector load instead of a load. You're going to do a vector add instead of an add. And all of them have a suffix on them, like .U8. That stands for unsigned 8-bit. Okay. And so there's also U16, U32, S32, S16, S8, right? I don't think you can do 64, but those are your options. And so that basically says, are we going to treat this quad, if we have got quad register 0, are we going to treat it as if it was, like 4 different integers, int1, int2, int3, int4. Are we going to treat it that way, or are we going to treat it as if it was like 16 different chars? Char 1, char 2. Do you guys understand? So every time you do an operation with the vector, in any vector operation, you have to tell it, is this a vector of chars? Is it a vector of ints? Is it a vector of halves, shorts? This line of code here, vector load, it's going to load from this pointer with write back. That means move the pointer to the right. After you do the load, the pointer moves to the right 128 bits. So it's going to load into Q0. It's going to load, in this case, 16 different chars. So if R0 is pointing at a character array, that will do 16 loads in one operation. You don't like the syntax? That's you got to have it. Like, because it has to know, am I loading, am I loading, well, I guess for load it doesn't matter, but if you're doing an add, you have to know, am I adding 8-bit numbers, 16-bit numbers, or 32-bit numbers, because when they overflow, it needs to not affect the next column. You know what I mean? Like, if integer 3 were to overflow into integer 2, that would be bad. And so what happens is that anytime a bit tries to overflow like that, Neon stops it from overflowing. What's the exclamation mark for? That's called write back. I've mentioned this a couple times. After it finishes the load, so let's say R0 is a pointer to like a char array, like for your image processing, it's a pointer to a char array. After it finishes loading these 128 bits, the pointer moves 128 bits to the right. That way you don't have to have a separate add. So it saves you add R0, however many bytes it loaded. So if you wanted to, let's say you wanted to divide everything by 2. Let's say that you wanted to do a image darken. What you could do is you could load 128 bits. This loads 16 bytes, or 16 bytes, let's say, from the pointer held in R0. And then the pointer moves to the right. But we've loaded 16 different RGB values into Q0. Let's say we want to divide them all by 2. Then we do this. Vector shift right, treating it as if it was all unsigned 8-bit integers. So shift right, Q0, Q0, 1 bit. And so all 16 of those chars will get right shifted 1 bit. And so all of them get divided by 2. Okay. And they don't fall off into the next channel. They get the rightmost bit just vanishes. They go away. Okay. Do you guys understand that? You know how to do a arithmetic shift right, Zach? Okay. So what we have is a vector register. A vector register is a big 128 register. Now let's say it's got, we sort of think of it as being 16 different things. So let's say we've got our RGB value of 10 and 7 and 8 and 100 and 50 and 60 and 1 and zeros. If this is Q0, so Q0 holds all of those numbers in one register. After we did the vector shift right, then the first byte will now be 5, the next byte will now be 3, the next byte will now be 4, the next byte will now be 50, the next byte will now be 25, the next one will be 30, 0, and all these will be zeros. And so it does a division by 2 on 16 different chars all at the same time. What if they're not all 8 bits? Well, then you'd change the suffix, right? But for your image processing assignment, it's all going to be unsigned 8-bit. So it's nice. But yeah, you could do a signed 32-bit. So you change that. You would change the suffix right there. If you're doing 4 32-bit numbers, that'd be an S32. It's splitting up the register, exactly. Yeah, you have one giant register, but it's actually a bunch of smaller registers, kind of, sort of. And so that suffix there, this number here means how the register is being split up. If you wanted to access 9 only, 9 only? What do you mean 9 only? Like the ninth element out of this? Int 9? I'm not following. You mean like channel 9? Like this one or something? The 9th element doesn't matter. Yeah, there's a command for that. You almost never do. Right? Like, because the whole point of this is doing batch processing. You've got an image. It's got 4,000, chars in it. And so you're going to load 16 at a time, divide them by 2, and then write them back. And so you the whole point of it is that you're just doing the same operation on all of them at the same time. There are commands to load individual channels if you need to do that. But that's, if you're going to do that, just use a regular integer, like R, right? If you need a specific int, you just load it into the R register instead. The whole point of the neon registers is you batch process things. See me. So here is code to here is a darkening code. So this is a working image processing thing. So this loads 128 bits into Q0. Color's different now. Check you out. So that's going to load 16 chars. It divides them all by 2, and then it writes it back. So R1 is a pointer where the output array is. This is the input array. And then it just keeps going until R0 crosses the finish line. So R3 is the end. That's the end pointer. So R0 is the begin pointer, R3 is the end pointer, and what's going to happen is that this will load from R0, the pointer moves to the right, divide by 2, right to the output pointer. The output pointer moves to the right, and we just keep doing that until R0 crosses the finish line. Once it crosses the finish line, we're done. And so this is 5 lines of code that will darken an entire image. Okay. So I think we'll probably have to pick this up on Tuesday because there's not quite enough for you guys to get on yet. So I'm not even going to deploy the homework yet. We'll just I'll just give you guys off the weekend, or maybe I'll deploy it. You guys can work on it if you want. I'll make it do 2 Tuesdays from now. Okay. So in the meantime, get a partner and talk about what kind of image processing you want to do. I guess I'll push it out, but there's a little bit more you guys need to know about this. Yeah. So we'll just pick this up on Tuesday. So I'll give you guys plenty of time to work on this assignment. It's a fun assignment. I want you guys to have time to work on it. Okay. Looking for partner, DM me. All right. So that is it for today, guys. Big takeaway points for today was Flynn's taxonomy. First half of the class, you guys learned a lot of useful C++ stuff. You learned about preprocessor directives and passing command line parameters to a function and how to debug programs. Second half of the class, we talked about Flynn's taxonomy, SIMD, big term, and then we started getting into Neon Genesis Evangelion, which is the ability to do 16 divides all at the same time, which is pretty cool. All right, so that is it for today. I'll get the assignment thrown up and just get a partner. It's more fun with a partner anyway, so I'd recommend doing it. All right, see you guys.